from the Space TimeLab in UCL. Well, I'll be talking about matching GPS data to transport networks. So basically the problem is if we have like a typical network, like a road network, we have some GPS data found all around. The problem is obviously with GPS is the GPS errors. A typical process that happens is basically matching everything to a road network or GPS data to a road network, which is typically called the process of map matching. However, another problem is if we have more than one network, like we have a rail network and we have a road network. So how do we match that? How we use that? How do we just match the nearest network, or how do we select the network to match to? And we can regard that as a process of network matching rather than map matching. So basically, if we kind of put that into words, it's network matching as a word could as a process could be the process of matching any positional data, which usually has error in it, to the respective transport network. So why is this useful? It's useful for, again, to select which network to match to analyze network usage. If we have like lots of road GPS data without any other metadata, which network does each trip or each part of the trip or each stage of the trip belong to? And as well it's useful for the detection of the travel mode from GPS data. Again, why is that important? It's important at the higher level to run model split analysis, studying tourist activity, assessing the impact of a strike on a transport network, and seeing which networks get affected. Existing methods basically, not lots of research really has touched very, very strongly in that point on addressing the network matching problem. However, a couple of studies here and there kind of worked on similar or parallel problems. Some of them, however, lacked a little bit of studying the geometrical relationships between GPS points with the transport network that a trajectory is traveling on. Because lots of them study, for example, the entrance of GPS records into GPS trajectories into urban canyons, and then coming out and seeing that the speed, for example, spent within an urban canyon was, let's say, 5 minutes, and that means that it's probably a car, most probably a car than any other form of network. So the inference was, or the detection of the correct network was based on speed or travel time on the network or whichever network. It also there was a little bit of disregard to topological movement. So lots of the movement or the routed information of every network wasn't really used a lot to kind of address that problem. So that's obviously what we're gonna tackle on. So our study area, or how we the area that we're gonna run our method on was the London network, and obviously that's because it has many data sets, many transport network data sets. So if we break these down into different networks, you have the rail network, underground network, the road network, bus network, and the OS urban paths network, which has all the the extra paths of local network. However, you have the bus modes and the walk modes are sort of still on parallel. They also use the road network, so the modes are sort of distributed in sort of that way. So we choose 3 networks to run the network matching on, which are basically the bus network, the underground network, and the rail network. Again, the data was provided by TfL. That's the bus network data. The underground network was provided online, free to use. The train network was OSN data. So basically, the concept of the work we've done was breaking a specific trip into different stage, every stage containing a different travel mode. So breaking basically a specific trip and a typical trip like that into walk-in and non-walk-in stages. That example that was on the ground, but it's regarded as an unwalk stage. So we test every non-walk stage as into which network it should be matched to. So we start with the first bit is basically just understanding the time and distance threshold. So we set time and distance thresholds, trying to understand or trying to set for every network type what is the maximum distance that a trajectory can be far away. I mean, this sort of the error generated by each sort of trajectory on any specific network, and setting a maximum threshold for that distance or that displacement distance, and setting a threshold as well for the time durations spent, like let's say on the underground, for example. So least trips could take a specific time, and that's sort of the minimum time threshold that we can assign for a certain stage to go for. Another thing is basically the routing information. So we attempted to use the routing information in the sense that if you have several networks, like in this way, you might find that that non-walk stage is closer in terms of distance, is much closer to the rail network, however, or the underground network. However, it seems not to follow one specific route. So again, the route information kind of makes that separation. So basically, we have a big data set on Oracle database, and all the work is done through R. R kind of calls all the data from Oracle, does some stuff in Python using the ArcPy Esri library. Goes back, does other stuff in R, and then sends back, updates the stuff in Oracle. So that's sort of the hierarchy of how things work. So in Python, we basically use lots of methods to run proximity analysis, to find the nearest networks, to rank the nearest networks to every GPS fix, and rank them to the closest 40 network links. And in R, we kind of use loads of libraries to deal with Oracle, to deal with DBF files, with shape files, with other things, with strings and so on to work in R. And we basically do both the phases of both the processes in R, which is basically assessing the time and distance thresholds and testing the route information. So basically applying that to the underground data. So basically we test the non-walk stages to be matched to the underground network. As you can see here, for example, the points in red are basically the points that were actually matched, and that was district line in London, and they were properly matched. So the accuracy of detecting underground trajectories was around 77% or 78%. Little confusion with other modes, a little bit confusion with bus, but it was minimal confusion. However, we go to the bus network, which is a bigger network. There's lots of overlap with the road network, so with cars and bikes. Obviously, walks were already disregarded. And the accuracy goes down a little bit to 55% to detecting the bus mode or matching to the bus network. There's some confusion again with a little confusion with the car and bikes network. Car and bikes mode, or choosing car and bikes to kind of be matched to the bus network. However, it's not that high still. In the railway, however, which is the extreme problematic network because it goes all through the UK rather than just London, it was matched properly because obviously that you don't find lots of clusters of the network within the UK, so it's much widespread, so it's easier to match. But on the other hand, a limitation is that we don't have any routed information for the rail network. And so you can see like lots of other confusions with other modes, and that's basically that kind of shows that the usage of routing information is quite important to differentiate between between the modes, because that's simply just saying if it's close to the network and if the whole stage is close to a train network, then therefore it is a bus trajectory rather than assessing like if it's moving around the network or not. So talk is really short, so that's the final slide. Good news. Conclusions basically is that the network matching addresses many needs of current research. Lots of applications regard this small thing to be something really key to solving lots of issues or cleaning data in lots of ways. Again, according to our test, it has very good accuracy achieves very good accuracy for detecting underground movement. Moderate for the bus, it may and obviously low for the train, which brings me to the limitation. That's because again the absence of RAID routing information in the OSM dataset. Yeah, the question is basically adjusting the thresholds according to the more data you get. You adjust the thresholds. The thresholds were basically used from the TfL annual reports or our Department of Transport as well for rail networks. So all these thresholds were set from annual reports, transport annual reports. Further work is basically integrating something like that, for example, with another system that classifies the travel mode from GPS data and kind of integrating that with that, or using that as a verifying stage for end studies that kind of aim at classifying the travel mode from raw GPS data, which is again part of the project I'm on, and this really acts as very complementary to the work I do, and alters the accuracy or enhances the accuracy by around 9%, the classification accuracy that is. So yeah, so that's pretty much it.
Thank you.